All right. So we'll kind of get started here today. We'll work through some material. We'll spend some time in Stata so that we should have everything you need to answer every single question on that problem set. So the stuff that we haven't covered should be kind of the last two questions. There's a question or two in the middle where we've talked about enough where we could probably figure it out, but I'll go over some examples that kind of look a little bit more so you can kind of maybe check what you did on those. And I'll pull it up and then kind of mention what those are. I have tried to reiterate throughout the first 2 weeks to start on this early and make sure we can get Stata working so we can open files, save do files, things like that, because I know that these issues come up, right? So I've got this problem set to be due, where we have it at, right? At the end of the day, Thursday, right? So I'll probably push this off to be the end of the day Friday, just to kind of give you a little bit of extra time. Since I canceled office hours on Monday, I am going to add an additional office hour tomorrow prior to the usual one. So I'll start at 8:30 instead of 9:30. And I'll get up an announcement about this. And then just kind of like last week, I'll have another 2 office hours on Friday morning. All right. So I'll push that due date off to be the end of the day Friday, just to give you another day. If you want to stop in last minute checks kind of on Friday, I'll have some office hours then. But we'll kind of dive into Stata later on in today's class. Another thing I'll mention off the top, do not do this now. I think there was maybe some confusion by a few people on the in-class quiz 1. So I'm going to reopen it today. Do not try to open it now. When we get to it at a certain point in the class, I'll reopen it. We'll kind of revisit this. And if for some reason, misconstrue what I said on Thursday, I'll kind of have a second attempt. Usually won't be the case for these in-class quizzes, but given it was the first one, and I was kind of just giving you the answers because we didn't quite get to the material, you'll have that kind of opportunity here today, okay? So we're going to start with, where are they at? These complete versions of the slides. And we'll kind of pick up where we left off. I mentioned last week as well, quiz 2, I kind of moved the due date from the original one. So I believe I have it set to be, well, let's see, the end of the day, Tuesday, I believe. Well, I don't have it changed here yet. I think I have it set to be, because we'll have covered all the material maybe today. If not, we'll just barely finish it up on Thursday. So that you should be preparing for that first quiz, and that'll be due kind of the following Tuesday. All right. So start preparing for that. The only kind of questions we won't be able to answer after today would be confidence intervals. But for the vast majority of those quiz questions, we should be kind of set to go on them, especially after today. Okay. All right. We don't want week 2. We want week 3. So any other questions for me before we dive into things? Let me make sure I made a list. I mentioned that, I mentioned that, I mentioned that. Okay. Any other questions before we get started here? Okay. So we kind of left off thinking about, or at least introducing this idea of hypothesis testing, right? So where does this come from, right? We'll talk about different types of hypothesis testing that we can do, but kind of to revisit where we left off and what we're really going to be doing today. So we said, and I kind of showed you an example in Stata where I said I won't ever expect you to do anything quite this extreme. But when I'm looking at the distribution of my sample mean, so this was the idea, if I take 1,000 different samples and I calculate the mean from every single one of those samples, I then kind of graph those out. As long as I have a sample size above, do we remember what value? 30-ish, it's going to follow a normal distribution. And it should be centered around whatever that true population mean is. Okay. Now, we said kind of the variance on these sample means is going to, sorry, I have standard deviation here. So the standard deviation of these sample means should be the square root of the variance, which will be whatever the original population variance was over our sample size. So this is where we said the higher the sample we get, the narrower that distribution got. All right, we kind of worked through that state example, going to prove this. I think I went from like samples of size 10 to 20 to 100. So here, a lot of the times, if I were to convert a sample mean into a z value, the number of standard deviations away the mean would be from the mean is always a z value. So z values represent the number of standard deviations away. It is the mean. So it's 0 standard deviations away. And then we can kind of convert these by taking the sample mean value we see, subtracting that mean, and dividing by this standard deviation. Now, what we started to kind of, I think I mentioned at the end of last class, is a lot of the times we don't have the population mean. The whole reason why we're taking a sample is because we don't have the population data. So what will end up being true is if we instead, we use the best guess that we have of what the population mean is, which is what was the sample variance that we saw? Or sorry, I shouldn't say population mean. The best guess of what we have of the population variance is the sample variance that we saw. Okay. So when we come down here, if we use that sample variance, we won't quite get a standard normally distributed variable. We'll have I mentioned at the very kind of end of last class, it's a student t distribution, right? So it's a very similar idea. It's just that we said the student t distribution, it depends on what our sample size was, right? So it'll be more or less varied depending on if we have higher or lower sample sizes. So we'll start out with this idea. I'll first start out assuming that we somehow know the population variance, and then really it'll take us like a minute to say what happens if we don't have it, because not a lot's going to change. So what we're going to do is say, okay, look, I know that as long as I get a sample size over 30, my sample means should be normally distributed around whatever that true population mean is. The problem is I don't know that population mean. So what I'm going to do is assume that it's a certain value, okay? So maybe this is the example like, I'm going to assume that the average height is 68 inches, okay? Now, I know that if I knew what that standard deviation was, or I knew what that variance was, that when I turn this into a z value, right? So let's say I take a sample and I see 74, right? When I turn this into a z value, I could then look up that z value in the table, and the table always told me the area to the left. So if this is in fact, if what I assume to be true is in fact true, if the true mean is 68, then the probability I see a value that is 1.29 standard deviations above the mean or anything further from that mean will always be the same, right? When we get to that z value point, when we look it up in the table, we're always going to find the same corresponding probability, right? So this z value of 1.29 really has an associated, we'll call it alpha, area in that tail. That area will always be, I think it's 0.0985, but we kind of say that one, it's approximately 0.1. This is one of the benchmark values that we're going to use, okay? So every z value we have has a corresponding area in the tail that's always going to be the same. So what we're going to do is assume that the true mean is a certain value, and then we're going to say, okay, look, if I ever find a sample mean, and let's just assume for the sake of this example, 74 is 1.28 standard deviations away. If I see a sample mean that's greater than that, it's going to correspond to a z value that's what? Greater than 1.29, and the area to the right of that will always be less than 0.1. Okay. So if I ever see a test statistic greater than 1.29, I know the probability I saw that sample mean, if what I assume to be true is in fact true, the probability I saw a sample mean that far away from that assumed true value is less than 0.1. That's so unlikely that it must be my assumption was wrong, right? And it's not necessarily the case. We'll talk about type 1 errors here in a second, but that's the general idea. What I assume to be true is in fact true, then if I see a sample mean that leads to me to being a probability of seeing that or anything even more extreme or anything any more different from 68, that probability is less than this threshold I set, which was 0.1. The probability is less than 0.1 would be a percentage of 10%. There was a 10%, less than a 10% likelihood that it occurred if what I assumed to be true was in fact true, that my assumption is probably wrong, okay? So we're gonna start out with 3 types of tests, okay? And the first one I kind of already had drawn here, but I'll just kind of reiterate it. So the first one is gonna be, we assume that the mean is sorry, let me get my notation right. We're gonna assume that true population mean, is right one here. I want to do first a right tail test. So I'm going to assume that it is less than or equal to a specific value. Okay. So I want to see, is that population mean greater than a certain value? Okay. So here, if I'm thinking about a right tail test, right? Sure, I can switch back and forth here real quick. Whatever we want to find, we're going to assume the opposite is true. So here, if I have a right tail test, I'm assuming that the true mean is greater than a specific value. So when I write mu 0 here, this is like I'm assuming it's greater than 68, or I'm assuming if it's income, it's greater than 50,000, right? So we know that if I make that assumption, whatever this value is, I could really correspond that to a specific Z value, okay? Now, when I'm thinking about the 10% level, that Z value will always be 1.29. So whatever I want to find, maybe I think the average height in the US is greater than 68. I will assume the opposite is true, that in fact, it is less than or equal to 68. So if I see a sample mean anywhere in this range, it supports my null, that the true mean was in fact less than 68. Now, if I ever see anything out here, if I see a sample mean that corresponds to a Z value that's anything greater than 1.29, I know that the likelihood of that occurring was less than this threshold I set. So for a right-tailed test, anytime I see, and I'll use the absolute value here for once we get to left-tailed test. Sorry, I'm talking and writing. So we'll kind of think about this as a test statistic. So I'll write T-stat. Now this will eventually see we can do this for the standard normal or the student T. So when I write T-stat here, what we'll be using most often this semester is going to be values from that student T, but it still represents a test statistic regardless if I'm looking at the standard normal or the student T. So if I see a test statistic that an absolute value is greater than what we call this critical value, right? So the absolute value of my critical value. What that means is I saw a value that was more than 1.29 standard deviations away from whatever I assumed that true mean was, okay? And I think the way I drew this here, technically, if I'm assuming it's 68, I'm kind of assuming 68 is like the middle of that distribution, okay? So this would be the idea of a right-tailed test. If the sample mean I find has a test statistic that's any greater than that critical value that corresponds to that cutoff I was setting, in this case, I'm using 0.1 as the cutoff. We can use other ones we'll talk about in a second. Then I'm going to reject what I assume to be true, right? I found sample evidence that goes against that and goes against it enough to where at the 10% level, that probability of 0.1, I can in fact reject what I assumed. Now, we're doing the exact same thing if instead, let's say I have a left-tail test and I want to say, okay, look, I'm taking a sample and I'm going to calculate the sample mean. And I think that, so what I want to test for is that the true mean is, I don't know, less than this assumed true value of, I don't know, the average income in the US is less than 50,000. Let's say that's what I think is true. Well, the null hypothesis will always be stacking the deck against ourselves. We assume the opposite is true. So if I think the income is less than 50,000, I assume that is in fact greater than or equal to 50,000. So if what I assume to be true is in fact true, I'm going to use this value. That's where my sample means should be centered around. Okay. So if I ever see something, once again, I'm going to use this cutoff of 0.1, or the probability that the sample mean I find ever falls below 0.1, I'm going to reject what I assume to be true. So here, if I were to kind of correspond this to a Z value or a student T value, I know that the Z value that gives me an area of 0.1 is going to be not positive 1.29, but negative 1.29. And so then if I ever see a sample mean that's way out here, when I turn it into a test statistic or a Z value, it's going to have a test statistic that is a larger negative value, right? So I could think about here, it's like my test statistic. So only values that are larger in terms of they're a larger negative value than negative 1.29, would I then be rejecting the null for a left-tailed test? Or it's really the same thing. Because if I take the absolute value, if the absolute value of my test statistic excuse me, is greater than the absolute value of my critical value, I'll be rejecting. So this is why we take the absolute value, because then it doesn't matter if we have a right or left tail test, the decision is still the same. Okay. So this value that gives us 0.1 in the tail, that would represent our critical value. So one way you can think about this is it's the number of standard deviations away we would have to go in order to get that desired kind of cutoff probability in the tail. So my cutoff probability I'm kind of using in this example is 0.1. If I see sample mean that's any further than 1.29 standard deviations below that assumed true value, it must be what I assume to be true is likely not true. So I'm going to reject that assumption. Now, this is my right tail. This is my left tail test. If you're looking at this, what might be a good way to remember what type of tail test you have? It's based off of the alternative hypothesis, what I'm trying to test for, right? So if I have a greater than sign, that's a right tail test. If I have a less than sign, it's a left tail. Now, once we get to this step, nothing's really different, right? We're still comparing the absolute value of our critical value to the absolute value of our critical value. It's just that everything will be, instead of positive, negative, right? Because we're looking at the left side of the distribution, and we know that assumed true value for the mean would always have a z-value of 0, right? So nice and symmetric around that value of 0. Is this looking familiar? Things hopefully you talked about in 370? Okay. So with this idea in mind, we also have what other type of tail test? And this is one that we're really going to be using primarily all semester. So less than, greater than, or two-tailed, or is it equal to or not equal to a specific value? So if instead my alternative is I just care about whether or not that true mean is different from some value. So I don't know, 75.134, right? Any value I want to look for. I stack the deck against myself with my null hypothesis, which is that that true mean is in fact equal to that value. Well, here's where it gets a little bit tricky, because now if I have this assumed true value, I then take a sample and I turn that into a z-value, right? Well, notice if I want that same area of 0.1, right, the probability I saw a sample mean that was that far away from the assumed true mean or any further, well, now either side of the distribution would go against that null. Before, if I found a value here that it was above 50,000, that actually supports the null. There was only one side of the distribution that went against that null assumption. So now I'm going to have not just one critical value, I'm going to have two, right? I could be a certain number of standard deviations above or below my assumed true value now, and both of those would go against that assumption. Because now I don't care about what side of that assumed true value it's on, just that it's different from that value. So if I want the same area of 0.1 in these tails, what's going to have to be true about the number of standard deviations away I go? Well, if 1.29 gave me 0.1 for a two-tailed test, what total area would I have in the tails? I've got two tails, and there's 0.1 in each tail, 0.2. That's not my desired cutoff. I want 0.1. So if I want to test against this assumed true probability of 0.1, what do I actually need in each tail? 0.05. So my critical values are going to be, what's that z-value that gives me 0.1 total in my tails? I now have two tails. So the critical value is not going to be 1.29 or negative 1.29. It's going to have to be larger, right? If negative 1.29 gave me 0.1 in this left tail, to get 0.05 in this tail, I'm going to need to look at something that is a larger negative value. So I think if we do this one, I think it's 1.645. I might be remembering this incorrectly. I should know this off the top of my head. If we go back to the slides, hopefully I'm supported and I remember this correctly. But I believe that's the value we would find from that standard normal distribution.
In what instances would you choose like one versus the other, like the not equal versus less than greater?
It just depends on the type of example or question you have. So for a variable like, let me think, this is probably like left and right tail tests are probably more applicable in like medical fields, because you know a medication isn't going to, just by the nature of chemistry or something, you know it has to increase it. And so there you're just worried about, is it going to be increasing it by more than this amount? Like you know that it's going to like, and for instance, if I lower the price, what's going to happen to the coin demanded? It's going to go up. So my test shouldn't be that it is on either side. I should be saying, does it go up by more than a certain amount? Right? Now, for most times, if we don't know the relationship, we don't want to be assuming that it's anything, right? So I just say, well, is it anything different from a specific value? So more often than not, especially in economics, we're probably choosing two-tailed tests. In medical fields, things like that, you might be more likely to see left or right tail tests.
I might have missed out on this a bit, but like in the charts, it only gives you the like 0.0 and the value. How do you figure out if you have the decimal value in that?
That's just because I can remember it. But I would never ask you something, right? You're only going out to the second decimal. I'm just trying to do this. I think if you look it up in the chart, you end up with 1.65. So you would only ever, if I ask you a question, you only ever have to go out to that second decimal because that's as far as the chart goes out. If we're actually to integrate that function, we could go out to whatever decimal we really want to. But I'll hold everything to 2 decimals. That's a good question. Okay. Any questions here before I add in one more thing? So even though a two-tailed test kind of looks different in terms of the critical values that we're going to be comparing to, the ultimate decision doesn't change. Because if I see a sample mean out here, we're going to say, okay, what's the probability I saw something this many standard deviations away or any further? So I could find this probability, but remember, it's did I find sample evidence that was as far away from that assumed true value or even further? But if I have a two-tailed test, seeing a value of 1.8 standard deviations away, it was equally as likely for me to see a sample mean that was 1.8 standard deviations below. And now I don't care if it's above or below. So anytime I'm only ever going to have one sample, I can find the probability I saw that sample mean, but I have to remember for a two-tailed test, it would have been equally as likely for me to see something that far below. So when I have my test statistic, I'll find the area in the tail, and then I would multiply it by 2. But in terms of the critical value, all I'm doing is still comparing, is that absolute value of my test statistic greater than the absolute value of my critical value? And there it doesn't matter if I see a sample mean that's above or below. When I look at this absolute value, it's the same decision if I'm looking at a two-tailed test, a left-tailed test, or a right-tailed test, right? I'm just comparing the absolute value of that test statistic to the critical value. Okay. Any questions on that before we keep moving here? All right, I'm also going to jump the gun a little bit here, but I think it makes sense as long as we're doing work here before we go back to the slides to kind of stay here. So anytime I'm looking at these sample mean distributions, when I turn them into z-scores, anytime I see a z-score of 1.29 or this critical value of 1.29, it's always going to correspond to the area in that right tail. It's going to be 0.1. So this critical value of 1 is always associated with the probability that I'm choosing as my cutoff, or what we're going to end up calling alpha, right? That critical value of 1.29 always gives me alpha of 0.1 in the tail. So it's really, I could compare the critical values, or I could compare the probabilities. If the critical value is less than my test statistic, what must be true about the area to the right of my test statistic? It must be less than 0.1. Or anytime I have a test statistic, we're going to call that area that's more to the right, or the probability I saw that value or something more extreme, we're going to call that our p-value. So the same value of the test statistic would always have the same area in the tail or the same p-value. So I can compare the test statistic to my critical value. Anytime the test statistic is greater than my critical value and I would reject the null, what would have to be true? That alpha would always be greater than my p-value. So I can compare the critical value to the test statistic, or I can compare that alpha value I set, that threshold kind of benchmark value, to whatever my p-value associated with the test statistic is.
Basically, point that you want to know. Before point. That would you mean the threshold?
So I'm saying the sample mean I saw needs to correspond to the likelihood I saw it of being less than this value I set of 0.1, or that the chance I saw it was less than 10%. So it's really like just comparing. I mean, these are directly related. So it'll be like comparing the x values that have the same corresponding y values. I'm just comparing the x instead of the y's. I can compare my critical value to my test statistic. Anytime the test statistic is greater than my critical value, what would have to be true? That p-value is less than the alpha associated with that critical value. So both of these will be my rejection decision. We call this the critical value approach, and we call this the p-value approach. Now, the only kind of wrinkle that would get added in here is when I'm looking at a critical value for a two-tailed test, it's not what is going to give me alpha in the tail. It's going to be what gives me alpha total in the tails. So when I'm looking at a two-tailed test, my critical values that I see, I'm going to have two. One's positive and one's negative. And it won't be what gives me alpha in the tail. It's what's going to give me half of alpha in each tail. And then when I have my test statistic, the test statistic, in order to get my p-value, the area to the right of my test statistic won't be my total p-value. I'm going to have to take that area and multiply it by 2. So it's going to be kind of having half of the p-value in each tail. But ultimately, it doesn't matter. If I compare alpha to the p-value, if I divide both of them by 2, what's going to happen to that sign? Nothing. If I divide both sides of a relation, a less than or greater, if I divide by the same value, it hasn't changed that one of those values is greater than or one of those values is less than. Okay. So we can compare the critical value to our test statistic or our p-value to this desired alpha. Now, by setting alpha, we inherently are setting these critical values. Okay. Any other questions here? I'll summarize this a little bit in the slides, and then we'll kind of progress to thinking about how we might do some of this in Stata after I add in one more thing. Okay. So here, I've got kind of a setup summary, left, right, two-tailed test, right? Or what we call one-sided or a two-sided test. We're primarily going to focus on in this class two-tailed tests. So that we really just setting this up. I mentioned those one-tailed tests, but for the most part, we're going to be using two-tailed tests. Okay. Now we'll talk about when we're making this rejection decision, what makes it more or less likely we might reject the null. So part of what we're going to need for this is to remember when I'm turning this into a z value or a t value, right? This is where I said z values would only come if we knew the population variance. T values coming from a student T, or if we only have the sample variance, but it all works the same way, right? So thinking about this, when we calculate this test statistic, what we're actually dividing by is the standard deviation of the statistic we're looking at. So when we're looking at the sample means, to turn a sample mean into a Z or T score, we're subtracting the mean of those sample means, which is just whatever this assumed value we have is. But the standard deviation of the sample mean will be the variance of our sample divided by the sample size. Okay, so this will be our kind of test statistic equation, right? We'll think about this here in a second. I already mentioned kind of this critical value approach. I drew some things out for you here. This is just kind of a reminder that basically, if I looked at one-tailed test, I could say that, it's when the test statistic is greater or less than. A fail-safe is always just to compare the absolute value of that critical value to the absolute value of your test statistic. That would then make the right decision no matter what type of tailed test you have. So that's the way I typically teach it, right? You're just comparing the absolute value of that critical value to your test statistic, right? We already talked about what are critical values. It's the desired number of standard deviations away that give us a specific alpha in the tail. So if instead, I said, okay, I want the probability, I want to make it harder to reject. I want that probability if it's anything less than not 0.1, but I only want to reject if the chance I saw that sample mean is less than 0.05. I could do that. And that, once again, to the second decimal to your point, is 1.65, not 1.645, right? So I can set different alpha values, which inherently is going to set different critical values. If my critical value is higher, if I only reject when the absolute value of the test statistic is greater than the critical value, if my critical value is higher, am I going to be more or less likely to reject? Less likely, right? So I could think about this as, if this is the decision to reject the null, right? When that critical value is higher, is it more or less likely my test statistic is greater than that value? Less likely. And intuitively, that makes sense, because how do I get a higher critical value? I lower alpha. If I lower alpha, is it more or less likely the p-value is less than alpha? Less likely. All right, those will always correspond with each other. Okay, so I don't have to always use 0.1. I can use different values. I could set alpha to 0.05. I could set alpha to 0.01. If I wanted to be really stringent, I could set it to 0.0001. Right, make it really hard to reject the null. Okay, so just our typical values we would see for right and left tail test. They're always going to be the same value. It's just one will be positive, one will be negative. When we look at two-tailed tests, they won't quite be the same, because we now don't care about what side of the distribution it's on. We're going to have two tails, the critical values we need to get the same desired area in our tail or tails. It's going to have to be higher critical values, right, for these two-tailed tests. So these are primarily going to be the values we use the entire semester. Our benchmarks alphas are 0.1, 0.05, and 0.01, which would correspond to what? The probability we saw the sample mean we did, or anything more extreme, is less than 10%, 5%, or 1% likely. Right? That's why they are benchmark values. And those will always correspond to, as long as we have sample sizes over 30, these same critical values. So lucky for us, we don't have to use that table time and time again, because we're always going to have those same three benchmark alphas, which correspond to the same three benchmark critical values. Okay. So we already talked through how we make this rejection decision. I'm going to go a little bit further. We're going to use this test statistic, and I think here, well, I'll draw this out in a second, because we already did this. What I want to get to is, here are steps. We have to identify our null and alternative hypothesis. For us, we're going to primarily just focus on two-tailed tests. That part's done for us. We're not going to worry about left and right tail tests for now. Later on in the semester, we might bring them back. We then want to figure out what's our desired alpha. We said we're going to have these three benchmarks. We could compare to each one of them. I will then take the sample mean I found, calculate my test statistic. I would then take that test statistic, find the critical value associated with the alpha I'm setting, or that benchmark I'm setting. And then the fifth step, compare the absolute value of the test statistic to the absolute value of my critical value. If the test statistic is greater in absolute value, I reject my null. What I assume to be true, based off the sample evidence I found, is likely not true. Now, the p-value approach, we already talked through how we find that. So I'll skip ahead here. It's going to be the exact same steps, but once we get to step 4, instead of using the critical or the alpha to find a critical value, we're going to use our test statistic to find the p-value and then compare that p-value to alpha. So it's just two different ways of doing the same thing. Each approach should always lead to the same decision. Okay. In fact, you could do both approaches to make sure you get the same decision, right? It's a good way to check yourself that you didn't make a mistake. Okay. So at this point, where are we at on time? I want to just discuss some things that make it more or less likely we could reject the null. Okay. So let's assume I have these sample means. Here's the distribution of my sample means. And for the sake of this example, we'll just do a two-tailed test. Okay. So when I turn this into a test statistic, we're now primarily this semester not going to be looking at the standard normal, because the whole reason we took a sample is we didn't have population data. So I'm only going to have the sample variance, not the population variance. So when I go to turn this into a standardized variable, how do I standardize a variable? I subtract the mean of that statistic, and I divide by the standard deviation of that statistic. So what this will be for us is I'm looking at the sample mean. If what I assume to be true is in fact true, it should be centered around that assumed true value. Now, for the standard deviation of that sample statistic, it'll be the square root of the variance, but the variance will be the sample variance we found over our sample size. Okay, so let's think if I found this sample mean, and let's just, for the sake of this example, let's say, I want alpha to be 0.1, so that would be 0.05 in each tail, and we would use those critical values of 1.65 and negative 1.65. Okay. So if I turn this into a test statistic, maybe I'll reject in this example. Now, what are the things that make it more or less likely I would reject? Okay, so we'll kind of walk through what makes it more likely and less likely, and then we'll kind of summarize them. So there's kind of three things I could change here. If the sample mean that I find is further away from that assumed true mean. So if that difference is greater, what's going to happen to my test statistic? Assuming nothing else changes, my numerator will go up. So my test statistic will also go up if we only reject when that test statistic in absolute value is greater than the absolute value of my critical value. If the test statistic goes up, is it more or less likely I reject? More likely, right? It's more likely it's greater than that critical value. Okay. Now, excuse me, what if I instead change the sample variance? So let's say I found the same sample mean, but the sample variance I found was higher. What's that going to do to my test statistic? Yeah, this goes up. My denominator becomes larger, dividing by a larger value, decreases my test statistic, making it less likely I reject. If my sample size goes up, what's going to happen to my test statistic? Well, if this goes up, this fraction goes down. If I divide by a smaller number, my test statistic goes up. I am now more likely to reject the null. And this kind of intuitively makes sense. If there's less variance, right, in my distribution, so I'm going to kind of doing the opposite here. If there's less variance in the sample means I could see, then when I see a sample mean really far from what I assume to be true, it's likely that what I assume to be true is false, right? So smaller kind of sample variances would make it more likely I reject. If I take larger sample sizes, that's going to, we said, kind of pull that distribution, make it less varied. Then finding that same sample mean, it should now be less likely, or more likely what I assume to be true is in fact true, right? And I would be, with higher sample sizes, more likely to reject there. Okay. So these are kind of, we could think about things that change our test statistic and make it more or less likely we would reject. Now, there's one additional thing that doesn't show up in this equation that would make it more or less likely we reject. What might that be? So it's not going to be something that changes the test statistic. How do I find critical values? It's what is associated with alpha. So if I set alpha to 0.1, right, that gave us these critical values. That gave us 0.1 total in a two-tailed test in our tails. What if I instead want to go to what we call a higher level of significance? So instead of setting that probability, that threshold at 0.1, I'm going to set it at 0.05. That the probability that the sample mean I found, that there was a likelihood I saw it of 5%, what's that going to do to my critical value? If I want 5% in the tails, my critical values are going to have to be larger. So if I want a smaller alpha, my critical values are going to be higher. Is it more or less likely I reject? Less likely. That same test statistic, if my critical value is higher, it's less likely that it's going to be greater than my critical value. So we have four things that can change this rejection decision. The threshold we're setting, it's harder to say things at higher levels of confidence. I might be able to reject something with 10% confidence, right? Or, sorry, I should say it this way, 10% significance, which corresponds to 90% confidence. But I might not be able to reject it with 5% significance, or I can't reject it with 95%, right? And then these other three things that we talked about would change our test statistics so that seeing the same sample mean would lead to being more or less likely to reject the null, okay? So these are our four things that could change our rejection decision. Okay? Once again, hopefully this is looking like somewhat of a review from 370, okay? So with this idea in mind, I'm going to quickly show you something. We'll skip over this for a second. If we have time today, we'll kind of revisit it. Kind of related to what we've already talked about, but I want to make sure we have time to do some work in Stata. And so I'm going to show you something, right? And then kind of do some hand waving so we can focus on it in Stata. And we're really not going to have to do this by hand, okay? So we can do hypothesis testing, not just for a sample mean, but for any statistic, okay? So you could almost think about if I was interested in the difference between two groups, right? So I think here, or do I have it set up here? There we go. I skipped over it. Let's say I want to know not like is the sample mean of one group greater than a certain value, but is this group's mean, is male height greater than female height? I want to compare two groups. The statistic I'm looking at is no longer the sample mean. It's going to be the difference in those groups' sample mean. So the statistic I'm now looking at is that difference in the sample means. What we usually do in these, types of tests where we're comparing two groups, once again, we don't want to assume one is larger than the other. We just care if they're different from each other, right? So I want to know, does group A have a mean that's different from group B? I'll stack the deck against myself and assume they have the same mean, that difference is in fact 0. Yeah. So I'll kind of talk through this, right? So we've got the difference that we're looking at. So maybe I'll set it up this way to kind of give you a stacked comparison. So when I was calculating the test statistic of one group sample mean, I had an assumed true population mean that it would be centered around. I then divided that by the standard deviation of those sample means, which was the the square root of the sample variance over my sample size. If I want to create a test statistic instead for a different statistic, so here I was trying to do that for a sample mean. We'll call this the test statistic for a sample difference. So if I follow the same line of thinking, I'm no longer interested in, is this one group sample mean? I'm now looking at the difference between two groups sample means. So my statistic I'm looking at is that sample difference. Now we said what we'll assume is that true difference, or the assumed true difference, is equal to 0. We're always going to have a two-tailed test in these examples. We just want to know, are these groups different from each other? Okay. So instead of subtracting the assumed true mean, I'm subtracting the assumed true difference, which will always be 0. So I can really do what? Ignore that. Subtracting 0 doesn't do anything. Now, when I divide this, I need to be dividing by the standard deviation of the sample statistic I'm looking at. Okay. So this gets a little bit, this is where I'll do a little bit of hand waving. We won't go through the mathematical proof, but I think intuitively it makes sense. If this is the standard deviation of one group, if I'm looking for the standard deviation between the difference in two groups, what I'll essentially be doing is saying, take the variance that exists in group 1, take the variance that exists in the sample statistic for group 2. Well, if there's this much variation in group 1, this much variation in group 2, the variation in the difference would just be the sum of those two things, right? So it's almost like I'm taking the variation in group 1, variation in group 2. The total variance when I'm looking at the difference between those two groups would be the sum of those two. And then if I want the standard deviation, what do I need to do? Take that variance and take the square root. So we're still following kind of the same pattern. It's just that the sample statistic we're looking at is a little bit more complicated. It's not just one group sample mean. We're looking at the difference between two group sample means. Okay. But if I was to draw this out, now instead of one group sample mean, I'm looking at the difference. It should be centered around whatever I've assumed that difference to be. Here it's often 0. And that standard deviation will be the square root of each group's sample variance divided by that group's sample size. Okay. So it's just instead of one group, we've now got 2 groups. Okay. But now once we have a test statistic, we do the rejection the exact same way. Compare the critical value to our test statistic, compare the p-value to alpha. Okay. So what does this look like in Stata is going to be the next step. So any questions on going from just one group sample mean to thinking about this difference? Hopefully I answered your question there with what was in the slides. And I think in the slides I was using y instead of x. It's just notation differences. You could use any, I could call this the average of q or what, it's just a variable, right?
So the test statistic that you're using on that graph would be the difference of the two.
Yep. So let's say I looked at male and female height, and the difference I found is not 0. Let's say it is 2.45 inches. What I'm doing when I calculate this test statistic is I'm turning it into a student t-value. Whatever that student t-value is, I then find the area to the right of it, multiply it by 2, if it's a two-tailed test, right? Because it would have been equally as likely for me to find a difference over here, and that would represent my p-value. I could then compare p-value to an alpha of 0.1. I can compare it to an alpha of 0.2. In fact, let's say I found that this p-value, the probability I saw this sample difference, I go through and I find that it is 0.03. What levels can I reject at? Here's where, moving forward in class, we can use the critical value approach. And I might ask you questions on that first quiz using that. But as we progress throughout the semester, we're really going to be relying on the p-value approach. It's much easier, right? Because if these are always my same benchmark alphas, when I have that p-value, it doesn't matter what alpha I'm comparing to. I found the same sample difference, so my p-value is always 0.03. If I only reject when the p-value is less than alpha, will I reject at the 10% significance, or what we call the 90% confidence level? No. Will I, or sorry, of course, yes, 0.03 is less than 0.1, so yes. Will I reject at the 5% significance or 95% confidence level? Well, 0.03 is less than 0.05, so yes. Will I reject at the 1% significance or 99% confidence level? No, or what we would say, we fail to reject, right? So once I have that p-value, I can very quickly make my rejection decisions at each one of these benchmark levels, okay? Any other questions about this before we move to Stata here for the remainder of class, probably? Yeah.
Do researchers do a variety of alpha values and explain?
If you go out and look at an academic paper, almost every single time what they'll report to you is essentially what they'll use. This will make a little more sense once we get to looking at linear regression. They use stars. So they say at the 10% level, if we can only reject at the 10% level, that's 1 star. This would be an example where I can reject at the 10 and the 5%, so they would put 2 stars. If I can reject at all levels, 3 stars. So they're almost always using those same 3 benchmarks. What some researchers will do to get a little bit tricky is they'll say they can reject and they'll change it to 20% confidence. Well, I mean, if I start to lower the if I start to increase alpha, right, it's going to be let's say I found a p-value of 0.7. Well, how can I make sure I reject? If I set alpha to be 0.8, but remember, I was saying 0.1 corresponded to a 90% confidence, right? 10% in my tail, 90% outside of it. So this was like a 90% confidence level, 95, 99. If I choose an alpha of 0.8, and I'm not saying they're ever going to do anything this egregious, but if I did, what's my confidence level here? 20%, that's pretty low, right? That's, I could reject just about anything, based off if I'm lowering the level low enough. So we primarily, you'll only see researchers kind of use these same 3 levels. Yep. Okay. Any other questions? Okay. So let's go here. And with this in mind, I'm going to pull open this do file editor in Stata. Okay. So this is where I'm going to try to reiterate. If you're here and you open up a data set, if you go to File, Save, you're only saving the data. You won't save any of the code that you put into your do file. So once you open up this do file editor, and I put up a file for this week, and it was that same review of statistics, you could pull open the old one if you want to. I just put a new one up there that kind of corresponds to like, this is where we started working on this in week 3. So it's that same review of statistics. I'm just going to make some edits here now that we're in week 3. Okay. So it's the same file as we had open before. We've done all of this stuff. So we're going to scroll down to, we did scatter plots, we standardized, blah, 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 blah. I'm going to go all the way down to line 74, where we start looking at this election data. Okay. Now, to make it easier on you, instead of importing this election data file, which we kind of walked through how you do this with the CSV, similar to an Excel file, I uploaded for this week. Where is it at? Did I forget to add it here? Looks like maybe I did. So I know I put it under files. Well, it should be up here. Did I not save it? Nope. So what I can do real quick is go to week 3. Did this before class, so I know it's sitting here. This will open up for me. Well, maybe. Unless I bog down the computer here. OneDrive. Oh yeah. So looks like maybe I lost some connection here. Of course, now it's trying to pop this up. There we go. All right. So let me go here. Go to files. Why am I getting this view? Go to files. There we go. Well, week 3 materials. I'll move this election data here. Throw it. This is where I hate doing things on this computer. All right, there we go. So I've got, no, that's not the file I wanted. Hold on. Oh, it's because my OneDrive didn't save it. I didn't really want to waste time doing this, but it looks like we're going to have to. Well, this might be good review. So I guess we're getting some review in here. All right. So looks like my OneDrive for some reason is not syncing. So we will close this. So let us close it. So I saved this as a .dta. I'll upload this after class. I'll kind of show you kind of what you could do. So I have my global path here. I'm going to set this to be my week 3 file. So I'm going to run this. This is where for you would primarily be putting, and I think I had it up here when we did this other example. You should like make it something simple, right? You don't want to have a bunch of subfolders, or if you do, you're just going to have to change this every week. So this was my subfolder file path. I'm then going to open up or import that Excel file. So that's the old one I gave you. I'll upload a .dta just to kind of show you, it makes it easier kind of moving forward. So if I import this, we'll wait. Oh, what didn't it like? So I have my global path. Let's see. Might have set it different. So we'll go to Excel, browse. Here's my election data. Looks like something's wrong with my OneDrive. So this is going to be fun. Because it's not able to access my OneDrive right now. So what can I do for you guys instead? Let's see if the old OneDrive files work. Let me see if I have that original election data. I had it back in week 1. Let's see if it'll open this up. Okay. What I wanted to make sure I did. So we go here. So if we open up that election data file, One thing that's kind of goofy with Excel files is usually in a data set, that first row is always your variable name. So you'll want to make sure you kind of have that selected. I already had that kind of entered into the code that was in that do file. So if you get your global path set correct, it should kind of open this up correctly. So looks like my file path that it's recognizing, for some reason, that week 3 folder is having some issues because it didn't sync changes I made earlier today. So if I get this file path set correctly, now when I go to import that election data, it'll open it up for me. What I would then probably do is save this, not as an XLS file, but as a .dta. So moving forward after this week, I'm always going to give you .dta files just like I did for that first problem set. So then it makes it kind of nice and easy. Once I have that as a .dta file, I can always just use that use command, or if I'm going here from the interface, not copy, file open. Now if I'm looking at these, I've got an election data, but it's a Stata data set. If I go to file open here, it won't recognize the old election data as an Excel file. So that's why I have to first import it and then save it as a data file. Now I can open it up. It gives me that line of code where it's using it. That's all I have here. It's just that I had my path set differently so that you could kind of copy and paste whatever your file path was. So once we have this election data opened up, and once again, if you don't want to for the sake of today, you could just import that Excel file and then kind of keep working with it. But if you save it as a Stata data file, you can then always just go to that interface and do file open. So if I've got this election data, I'm going to run some code here that we're not going to waste a lot of time on, which is I can rename variables. So this might just be helpful as you're working through problem sets because sometimes variable names come in and they're kind of complicated. Now here I didn't rename them anything crazy, but like they're kind of long here. I might not want to type this out every single time. So I'm going to rename that original variable, which was %20 Donald Trump. So this is 2020 election data. I'm just going to rename it Trump 2020. That's all the rename does. Takes this name, change it to this. So if I look at my data set, when I see this %20 Donald Trump, right? If I then run this line of code, it changes the name. That's all it did, right? I'm going to do the same thing. If I try to run it again, well, now that variable doesn't exist. So anytime I rename a variable, if I try to rename it twice, Stata is going to give me an error. It says, hey, you already changed the name. The name of that variable no longer exists. It's now only called Trump 2020. Okay? So I can't use this rename command twice, or once I do it once, it's done. Right? Now I'm going to rename another variable, which was that %20 Biden, to just make it Biden 2020. Right? I'm then going to kind of move forward. Now we could look at the distribution of the variable. We've already done this, so I'm going to kind of skip over this step. But I could look at the distribution of any variable by using that hist command. So instead, what I'm going to do is say, okay, look, I want to find the mean of this unemployment rate or unemployment variable. So if I look at this data set, I scroll over here, somewhere in it should be, where do I have? Is it at the very end? Yeah. I have what the unemployment rate was, and I think it's in every single state county. That's all my observations. So when I'm in this do file, I can create a new variable. We did this already with the other data set that's equal to the mean of something else. So I want to create this unemployment mean, that is simply the mean across every county of that unemployment rate variable, right? So once I do that, it's going to give me a variable. And always adds my new variables at the very end. So the mean unemployment in 2020 across every county in the US was 6.32%. Okay. I'm now going to create a variable that I call high unemployment. This is going to be, I'm going to generate a variable. And if we want to create a dummy variable, so this is just a 1 or a 0, right? When I use the gen command and I have this new variable high unemp or high unemployment, I'm going to set it equal to a 1 if the statement in parentheses is true. So if that county had an unemployment rate greater than the mean, I've created this mean variable. If it has an unemployment greater than the mean, I want to put a 1 into that variable. If that statement is not true, or the county had the mean unemployment or anything less, it's going to put in a 0. Right? So when I run this code, now we can kind of see anytime unemployment was below the mean, there's a 0 for those counties. Anytime unemployment was above the mean, this variable is a 1. Okay. Now, what this is going to allow me to do is essentially I can identify maybe differences in the voting patterns of high versus low unemployment rate counties. Okay. Sounds kind of similar to what we were talking about, a test between two groups, right? Is their mean different? Now, some other commands that we've talked about, I could use the sum command. Notice if I run this sum command and then go to stata, the minimum is 0, the maximum is 1. That makes sense. It was a dummy variable. Now, the mean of 0.448 means that on average, about what, 45% of the counties had an unemployment above the mean, right? Because if I take the mean of a 1-0 variable, essentially what that's telling me is the proportion of observations that had a 1. So if I then kind of also, I could use what I don't think we've talked about yet, which is a tab command. You won't want to use the tab command for a continuous variable, because what tab does is it tells you the number of observations that have this specific exponent. So if I did tab unemployment, it would tell me the number of counties that have 0.01, the number of counties that have 0.02, the number of counties that have all the way. That's going to be too much to look at. But if I have a dummy variable, when I use this tab command, it's simply going to tell me the number of counties that had a 0 below mean unemployment and the number of counties that had a 1 above mean unemployment. If I look at that, sure enough, the percent of counties that have above mean unemployment, about 45%, the same thing as the mean of that dummy variable. Okay, so kind of two different ways at getting at the mean of a dummy variable there, right? I can use the tab command or the sum command. Now, I had this kind of set up for low unemployment rate. Let me make sure. What did I do? My t-tests down here. We'll create these, but we don't really have to focus on them. This is where it's kind of nice if I give you guys the code. This is going to do the exact same thing, but it's going to create a dummy variable whether or not they had low unemployment. Hopefully, this should just be the exact opposite of when I had high unemployment. So we're just going to run these 3 lines of code. Now, if I generate this where it's low unemployment, I should get the same values as I had before. It's just that now this variable is going to be a 1 whenever it is low unemployment versus high, right? So it's just a different way of doing the same thing. So if I kind of tab this command, now look at, oh, if the proportion of counties that had high unemployment is 45%, the proportion of counties that have low unemployment should be 100 minus that, right? So I'm just creating a variable. It tells me the same information. It's just slightly different. So I've got this low unemployment dummy variable. I could look at the distributions. Here, we're not going to kind of focus on this for today, given the sake of time. I could then do things like, okay, we have this by sort command. So what this does is it will take this variable of low unemployment by every single value for that variable, which for us is just a 0 or a 1. It either had low unemployment or it didn't. It will tell me, or it'll summarize the percent of that county that voted for Trump, or summarize this variable. So what is that going to give me? It's going to give me each group's sample mean. Remember, when we talked about earlier, we wanted to look at the difference between two groups' means. Here's how I could get their means. So by each value, when it had low unemployment and when it had low unemployment or when it had high unemployment, the means of those two groups, the proportion of those counties that voted for Trump, what counties had a higher percentage that voted for Trump when unemployment was identified as low or below the mean? So this was like at the time, it must have been that counties that had low unemployment must have thought Trump was going to turn things around, right? We could insinuate that, or at least something about them was correlated with the fact that they were going to vote for Trump, right? So we see there is a difference in these two groups' means, but can we say that there is a statistically significant difference? If we run this hypothesis test, can I actually reject the null, which is that that difference is equal to 0? Okay. So how do we do that in stata? So if I come down here, I could generate group means. We're going to skip over this for today. It doesn't. We want to get to something that's a little bit more decipherable based off what we talked about today. So we're going to skip down here. I think I had some other variables created just out of interest. So I'm going to generate this dummy variable, which is, did the county have a high proportion of individuals considered white? right? So I think I set this pretty high. Is it above 80%? And I think here white was kind of, did it have a, percentage of white people identified as white or Caucasian above 80%? So we're going to create that variable, which is a dummy variable as well. We're going to create a high income kind of variable, which is, did they have an income greater than 75,000? So it's another dummy variable. And then we're going to generate this other one, which is if it had high income and it was a high percentage of white individuals in that county. So we can use multiple if statements, right? So now I want to create a dummy variable that's equal to 1 only if the county had high income and had a high proportion of white individuals. So what I can do is create this new dummy variable that's equal to 1 if the following statement is true. So if I want to have 2 conditional statements, the first is, was this a high income county, right? So here, I kind of use this just to kind of remind myself I wanted to show you this, even though it's not the variable I created. If it was a high income county, let's say I wanted to set this or have this so that it was, right? This income high was only 1 if income was above 75,000. Let's instead do, if this high income county, let's do low income. Well, if income high represented when they had above 75,000, what would mean that it's a low income county? If it was less than, or if this high income variable was not equal to 1, but not equal to 1. So anytime we want to do a not equal to, instead of this is a exclamation point equal sign. That's just the syntax. Okay. Now, if instead I wanted my original high income, instead of being not equal to 1, I want this to be equal to 1. I need to use a double equal sign. Once again, that's just the syntax of Stata. Okay. So maybe a good thing to kind of write down. This is where if I was doing things maybe in class, for a not equal statement, I want that. For an equal to statement, I need a double equal sign. Okay. So here I'm going to create this dummy variable, which is only equal to 1 if the county had high income, or the high income variable is equal to 1, or, right, they had a high proportion of white. So once again, if I want to do an or statement, that is going to be a vertical line. If this is true, or this is true. If I instead wanted to do an and statement, well, that one's kind of nice and easy. I just use the and sign, right? I would replace this with and, okay? So we can start to use conditional statements to create variables. These are going to be, this is kind of the syntax of Stata, okay? Any questions on anything I've said up to this point? Once again, just kind of trying to get us more familiar with Stata here. So I could look at kind of like use that by sort command just to look at the differences. So for instance, here, I'll create this variable and then by that variable, see, okay, if the county had high income or a high proportion of white individuals, the mean that voted for Trump was 69% in those counties. If it instead had low income or a low white population, a much lower percent voted for Trump. Okay, so that's the difference in my means, but can I reject the null? Is that sample difference I found significant enough to say the difference was in fact anything other than 0? Well, this is where we're going to use in a built-in t-test command. If we had to do this by hand, what would I have to do? Calculate the mean of both groups, get the sample variance of both groups, get the sample sizes of both groups, throw them in my test statistic equation, calculate my test statistic, look it up in the student t-table, find the corresponding area in the tail, multiply it by 2 for a two-tailed test. Now I compare my p-value to alpha. Stata will do all of that behind the scenes if we run a code like this. So this is use a t-test, or essentially test for the differences between two groups. I want to know, is there a difference in this variable? So is there a difference in the proportion of the county that voted for Trump in 2020? But then I have to say, by what? How am I identifying the two groups I'm looking for the difference between? I'm going to use this dummy variable, which is a 1 if it had low unemployment, 0 if not. So what Stata will do is say, take all the observations that had low unemployment, calculate the mean that voted for Trump, right? Take all the groups that had not low unemployment, calculate the mean that voted for Trump. Take the difference between the two, turn it into a test statistic, find the p-value, report that to me. Now, we add in this unequals option. There's some instances where you wouldn't use this, and I think we'll touch on one of them later on in the semester. We don't have enough to even for me to mention it at this point, but we're always going to like try not to make too many assumptions. So here, if we don't put unequal, what we're really doing is assuming that both groups had the same sample variance. That's likely never going to be the case. It's almost likely that any two groups we look at, their variance is going to be somewhat different, even if it's out to the second, third decimal. So I'm going to assume that these variances are different between these two groups. That's all that does. It's kind of just more of the syntax. Now, like anything in Stata, we can come here, do summary statistics. We can do I forget where this is at, a test of means, kind of go through this whole process, kind of choose our two variables, add in some group things. I'm always going to ask you to do similar things that we did in class. So instead of worrying about hunting through this interface, to test for the difference between two groups, you're always going to put the group that is this dummy variable, the ones and the zeros, as the second thing that's in this by command. The thing that you're testing for the difference between, that variable you want to compare the mean of both groups, that's what's going to come first. So the difference in the means of the percent of the counties that voted for Trump in low versus high unemployment rate counties, that's what this t-test command will do. If I run this code, notice it gives me left, right, and two-tailed test results. Okay, so we're going to focus on these two-tailed test results because we always primarily just want to know, is there a difference between these two groups? At what levels or what alpha values could I reject the null here? The p-value is 0. So is the p-value going to be less than alpha of 0.1? Yes, I can reject with 10% significance or 90% confidence. Can I reject the alpha of 0.05? Yes, 5% significance, 95%. Can I reject an alpha of 0.01? Well, the p-value is 0, yes, 1% or 99%. This is a very strong result. I can reject that the difference between low and high unemployment rate counties in terms of the proportion or the mean that voted for Trump, very different here, right? I can reject that value of 0 for the difference, okay? So this should hopefully line up with exactly what we were doing in class by hand. This is what kind of looks like the last two questions on that problem set, okay? Now, just for the sake of this, I could also do a test for the proportion of counties that voted for Trump, but between high versus low income counties, right? So this is where once we get these variables created, we can start to do lots of these tests. So if I go ahead and run this line of code, once again, what levels can I say that there was a difference in the proportion of counties that voted for Trump for high versus low income? All levels. The p-value is 0. I can reject that there was no difference. That was our assumption, right? We stack the deck against ourselves, assume there is no difference. We found a large difference here. So at every single level, we can reject that that difference is equal to 0. Now, what it shows you here is always the alternative hypothesis. So it says the alternative hypothesis is that difference is not equal to 0. Remember, the null is the exact opposite of that. We stack the deck against ourselves, assuming it's equal to 0. And then one that's a little bit more interesting here, maybe I look at kind of that proportion of the county that was high white. So I still get a p-value of 0. Nothing's really changing here. I think I added this one in. So this one I was like, I don't know. Does commute time really look any different? Like, is that going to influence how people vote? Maybe, because maybe it's inner versus like inner city versus urban areas. So I just created this new variable that was, do I have a long commute to work or not? I wouldn't think that the difference between those two groups in terms of their voting habits should be different. So if I go ahead and run that, okay, sure enough, at what levels can I say that the proportion or the mean percent of people voting for Trump in counties that had long or short commutes is any different from 0? Well, can I reject the null with an alpha of 0.1? Is my p-value less than 0.1? No, 0.2 is not less than 0. So can I reject? No, I failed to reject. What am I failing to reject? That the assumed true difference is 0. There is no difference in voting behavior of counties with long versus short commutes. That makes sense, right? I wouldn't think those two things are related. So just because we had some examples where we had a lot of p-values of 0, doesn't have to be that p-value is always 0, right? In fact, we could end up with one where we had like a p-value of 0.07 where we can reject at some levels but not others. So this t-test command is how you'll kind of complete those final 2 questions of the problem set. I know I'm kind of running out of time here. So one more thing I'll kind of mention, you can drop variables if you just don't ever need them by putting the name and drop here. This will just help sometimes clean up data sets if there's just too much to look at in that browser. We will finish confidence intervals at the beginning of class Thursday. That will be all you need to finish the quiz. The last quiz question is about confidence intervals, so I'm not going to open it up until after class on Thursday, but start looking at those practice problems, preparing to like take that quiz. It'll be set to be due the end of kind of next Tuesday. Try to get those problem set questions into me. Office hours tomorrow and Friday. You should have everything you need to complete them now. Other than that, stay safe, stay warm, and I will see you guys on Thursday.
The question,